Hi, grade 12s. Today we're going to start our Unit 2. So Unit 2 is atomic structure, and this is going to be lesson 2.1. Okay, so we're going to talk about sort of a general overview of electromagnetic radiation, and I'll touch on subjects that we're going to be talking about more in detail as we move through this unit. So first off, on the sheet I gave you there, you've got quite a bit of history there. The important takeaway of this is that there was a lot of debate over whether light was a wave or a particle. And so scientists have come to realize that, in fact, light behaves as both. Okay, so both of those are really the right answer here. We're going to talk about different terminology here for waves. Now, I think most of you have been in a physics classroom, so this is not new information for you, but don't worry if you haven't, you can learn this. So we look here, wavelength. Well, some terms here. So wavelength, elevation we're not going to use actually. Crest, so the crest would be at the top here. Trough is at the bottom, and amplitude is how high the wave is here. So this is a sinusoidal wave, and we know that waves travel all in this shape here. Okay, so flip your page over now on page 2. Excuse me. So the wavelength, we're going to use the Greek letter lambda here for wavelength. So wavelength is the distance from one crest to the next crest, or trough to trough. It's usually measured in meters. Not always. You can use different ways, of course. But so crest to crest, or you would have trough to trough, and that would be the length of your wavelength there. Another characteristic we're going to look at is frequency. So frequency is the number of wavelengths or wave cycles that pass a point per unit in time. So if we have our line there, you can see then that the top one, well, first of all, which one has the bigger wavelength? So this one has a large wavelength, right? But which one has the higher frequency? So how many wavelengths are going past a certain point? It's actually got numbers on here. So it's got let's start again, yeah, it's like basically 4 to 1 here is pretty close to the ratio of the short wavelength to the long wavelength here. So frequency, the SI unit is hertz, so Hz, but we often will use seconds minus 1, okay? So how many times things go through something per second. And so the relationship that we notice between wavelength and frequency is that they're inverse, right? So wavelength is going to vary with 1 over frequency. Oh, actually, let's talk about the unit for frequency. I tend to use F. Sometimes you'll see the Greek letter nu, which is like sort of this V with a little tail on it. But I think I'm going to use F, and you'll run into both notations at times. But important takeaway here, this is the relationship between wavelength and frequency. As one goes up, the other one goes down. Now, in 1900, Max Planck, now we're on the third page here. In 1900, Max Planck heated objects until they glowed. Then he studied the light given off by the glowing objects. He discovered that the frequency of light given off was directly related to the amount of energy released. So he said frequency is going to vary directly with energy. So if something has higher frequency, so these are our gamma rays here, high frequency in here, that would mean also high energy. And if we look here, our radio waves down here, we have very low frequency, large, but okay, there's another relationship here. So frequency varies with energy. So because those vary directly, we can also say then that energy varies with 1 over lambda. So the bigger the wavelength, the smaller amount of energy there is. So these two relationships we're going to use to talk about this chart here. So what this means, the biggest, if we look here, buildings, so radio waves, for example, these are huge waves, and if they're about the size of humans here, about 2 meters would be an average. 10 to the 2 to 10 to the 4 is the range for radio waves. So they're really large waves. So large lambda, large wavelength means they've got a very small frequency, which means they've got a low energy, which is good because we live in radio waves all the time. They're all around us. they don't really hurt, well, they don't hurt us at all. And then as we move this way on this spectrum here, we've got the different types of wavelengths, right? We've got microwaves, infrared, visible. These are the colors. This is what we see. UV lights, X-rays, gamma rays. And you'll know, a lot of you will know that X-rays, for example, have small wavelength, therefore high frequency, therefore high energy. And can X-rays hurt you? Yeah, you would always want to like be careful about how many X-rays a person is getting, because they can actually harm your body and harm tissues, right? And they're about the size, X-rays are about the size of atoms, and you can see the different sizes here. I like that chart, it's cool. Anyways, okay, now this is about halfway through page number 3 here. If we shine sunlight through a prism, we get a rainbow of colors known as a spectrum. And you'll see this often when you see if light happens to catch through a crystal, you'll see a little spectrum on the wall, for example. Now, when we get that spectrum, we get our Roy G. Biv. So you can write your Roy G. Biv right on that little spectrum diagram that you have in your notes there. So red, orange, yellow, green, blue, and violet. And sometimes we have an I in here for indigo too, which is kind of just in between the blue and the purple there. Now, each color in the rainbow represents light of a different frequency or wavelength. This is known as a continuous spectrum because there's no breaks in it. So this is a continuous spectrum. We go from Roy G. Biv, and as we go here, we go from, red is our long wavelengths, so our large wavelengths there, going to violet, which is our short wavelengths and much higher frequency. So our violet lights, violet here has the highest energy and frequency as compared to red, which is the lowest energy and frequency. And then we've got a range in between there. Now, this is our electromagnetic spectrum. So you can turn your page over here. This is on page 4 here. So the electromagnetic spectrum here, as you'll note, this little section here, this is the visible light. So this is what we see, okay? So it's a very small portion of the electromagnetic spectrum that's actually visible to the human eye, right? So we've got our radio waves here, again, which are our longest wavelengths, over all the way to our gamma rays on the left end here. So yeah, so just know the electromagnetic spectrum in general, and we'll talk more about this as we go, but this little section here, that is the visible light. That's what we can see with the human eye. Okay, so we're going to talk about something called an emission spectrum, and we will talk more about this in a lot of detail, so I'm just going to quickly gloss over this. So when an electric current passes through hydrogen gas in a tube, the gas glows, and this is true for all gases here. If the light produced by the glowing gas is focused through a slit and passed through a prism, a spectrum with distinct lines is produced. So this is called an emission spectrum, and what it does is it separates the wavelengths of light emitted by the gas. And remember, this is visible light in here, so we can see different colors. And so the emission lines for the element hydrogen, so this corresponds to the absorption lines for the same element, and we'll talk more about the absorption lines later. So this study of chemistry, this field of chemistry, is called spectroscopy. I took a whole course in spectroscopy in it's a 3rd year chemistry course in university. So as you'll see here, we've got these are different elements, and they've got very different emission spectrums, and they look different. They've got different lines and showing where the energy is being emitted, okay, at various parts of the spectrum. Now, one thing to note is that these are like fingerprints, so no two elements are going to have the same emission spectrum. So one kind of interesting story, in 1870, the bright yellow line in helium spectrum, so if we look at helium here, this bright yellow line was first seen when examining the light emitted by the sun. So basically the discoverers determined this was a new element and named the element helium, and it was named helium after the Greek sun god Helios. So 25 years later, helium was also discovered on Earth. I like that story. I like Greek gods and stuff like that. It's always fascinating. Some of you are probably like, you were into like Percy Jackson and stuff like that. It's fun. Anyways, okay, so flame test. Now, oh, you can turn your page here on the 5th page here. When some elements are burned, they give off a distinctive color of light. Now, some of you, there's little packages that you can buy. I think you can get them at like the dollar store even. And they're full of like this little salts, little powders kind of. And if you put them on a campfire, you get these really beautiful colors here. Now, what you're doing is actually a flame test, which is a chemistry thing. And we're going to do flame tests in the lab. Now, these different colors exist because this is due to the emission of light predominantly in that wavelength in their line spectrum. So the reason why these beautiful colors happen is because of this. These are emission spectrums here. So as you can see, just picked out a few here. So sodium, for example, has like this yellowy orange color. And if we look at the line spectrum of sodium, sodium's got a big yellow line there. Potassium here has got a violet color, and if you look at the line spectrum of potassium, we've got quite a few violet colors there. That's where it's coming from. Another one you'll often see is copper. Sometimes people put a copper tube in a campfire. Or a copper pipe, I should say. Copper has a greeny color, and if we look at this, we've got a sort of stronger yellow-green part of the emission spectrum. Strontium, again, strontium has like a reddish color. We've got a strong red line there. So this is why these colors exist. Now, northern lights are part of that, and some of you hopefully have seen the northern lights. They're absolutely stunning and beautiful. When I've seen them, normally I see the green color. And so what northern lights are, it's the same thing. It's basically like a big giant flame test in the sky. So we've got our different elements, and they're banging into each other, and when that happens, there's a release of energy. So as the energy is released, the electrons fall back to their ground state, which we'll talk more about later, and these colors are emitted. So often you see greens, reds, yellows, and those are all due to these elements here. So the oxygen, when the oxygen atoms are banging around, we get mostly the reds and the greens. And then when nitrogen, we get more of the pinks and the purpley, those colors, okay? Now, fireworks are another application of that. I took this picture. I'm very proud of this picture. It's one of my best pictures, I think. Anyways, this is like Canada Day a number of years ago. So fireworks are also an example of a big giant flame test. And so inside, you've got a diagram in your notes there of fireworks. So inside you've got different elements, and then as they burn, they release these colors, and this is why we see different colors of fireworks. Okay, so your assignment is questions 1 to 5, just on your on the back page there. So you can find all the answers to this in the booklet, and we will definitely go over that in class when we're next together. Okay, thanks everyone.